My name is Rifat Araprova, and I'm from Team Hamilton. And our presentation topic is three-dimensional viewing. So, at first, we're going to talk about some 3D viewing concepts. So, when we are modeling a 3D scene, each object in the scene is defined with a set of surface that forms a closed boundary around the object interior. For some applications, we may also need to specify information about the interior structure of an object, and there are different graphics packages that allow us to do that. Viewing functions process the object description that ultimately project a specified view of the objects onto the surface of a display device. So there are actually many processes that are common in both 3D and 2D viewing, and clipping routine is one of them. Clipping routine is basically defining a standard rectangular clipping window. And there are actually some additional tasks that we need to perform in 3D viewing, such as projection routines, lighting effects, surface characteristics, etc., as it needs more work than 2D viewing. So in order to set up a 3D scene, we can achieve that with three easy steps. So first we have to set up a coordinate reference for the viewing parameters, which defines the position and orientation for a view plane or a projection plane. And then we have to transfer object descriptions to the viewing reference coordinates and project onto the view plane. After that, we can generate a view of an object on the output device in wireframe form or apply lighting and surface rendering techniques to get more realistic shading of the visible surfaces. So let's talk about projections. So projection basically means transforming a point from a high dimensional space to a low dimensional space. And there are different methods for projecting a scene onto the view plane. Two basic methods are parallel projection and perspective projection. In parallel projection, we project a solid object onto a view plane by projecting points on the object surface along parallel lines. This is basically used in engineering or architectural drawings to represent an object with a set of values that show accurate dimension of the object. In figure 1, we can see an example of parallel projection, and we can see that if we project a box, it actually shows as a rectangle in the view plane. The next kind of projection I'm going to talk about is perspective projection, and that's actually more realistic. So, in perspective projection, we generate a view of a 3D scene by projecting points to the view plane along converging paths. It's called perspective because objects further from the viewing position is going to appear smaller than objects of the same size that are nearer. So, in figure 2, we can see an example of perspective projection. These are some examples of viewing softwares. So there are different kind of softwares that can help you to achieve 3D viewing, such as AutoCAD, Blender, Maya, Cinema 4D, and there are actually also many more like ZBrush, Shade 3D, SketchUp, and these are just examples of the UI of these softwares. And yeah, so in figure 1, you can see chessboard 3D modeling in Maya software, and in figure 2, it's actually a 3D model of a car in Blender. So let us talk about wireframes. A wireframe is the most basic visual representation of a three-dimensional physical object. A wireframe is what a 3D model will look like when all the polygon faces are removed and we only have the outlines of the components. It basically just consists of vector points, and those are connected by lines. These are some examples of wireframes, and as we can see, like we can use two different tables to represent a wireframe model, one vertex table and one edge table. The vertex table will contain all the vertex points of the model, and the edge table will show that how these vertices should be connected to get the final image. So there's an inherent ambiguity problem with wireframes. That is, wireframe models do not actually have any information regarding the depth. So it's difficult to realize which surface is in the front and which one is in the back. For example, if we take a look at this image, we can't really tell if corner A is in the front or corner B is in the front. So this ambiguity problem is called wireframe ambiguity. And in order to get rid of it, we need some sort of depth related information in these models. And one of the solution for that is using depth queuing. So in depth queuing, we render distant objects at a lower intensity than the near ones, and that gives an appearance of depth. In figure 4, we can see that the nearer lines are actually lighter, and as we go further, they kind of fade away. So this gives an illusion of depth. Okay, so now I'm going to discuss 3D viewing pipeline. And actually, generating computer graphics view of a 3D scene is very much similar to the process involved in taking a photograph. So at first, we need to choose a viewing position corresponding to where we would place a camera. After that, we need to choose viewing position based on what we are trying to display. Like if we are trying to display the front, back, side, or top of the object, we may also pick a position in the middle of a group of objects or even inside a single object. After that, we have to decide on the camera orientation, and finally, we can click the capture button. So this block diagram is a visual representation of the entire pipeline, and I'm just going to explain each part of it now. So at first, what we have is called model coordinate or local coordinate. So from that, we have to transform it to world coordinate. So we do that by modeling transformation that converts this local coordinate system into the 3D world coordinate system. And then that goes through the transformation to get viewing coordinates. After that, the viewing coordinate system defines the viewing parameters, including the position and orientation of the projection plane. So the two-dimensional clipping window corresponding to a selected camera lens is defined on the projection plane, and a three-dimensional clipping region is established at this point. And after that, we can perform some projection operations that are performed to convert the viewing coordinate description of the scene to coordinate positions on the projection plane. So after all of this is done, we can normalize these coordinates so that they are no longer device dependent. And after that, we can clip all the parts of the object that is outside of the viewing region. And finally, we can do viewport transformation to show it in the device. So we perform viewport transformation on that. And then after that, we get to display the final object in the display window. So this slide basically includes all the steps that I just explained. So I'm going to skip through it. And now we're going to talk about different kinds of 3D viewing parameters. So the first kind of viewing parameter that I'm going to discuss is view coordinates. So in order to establish a three-dimensional viewing reference, there are some steps that we can follow. So at first, we need to select a world coordinate position, which is P naught in this case. And this is called the viewing origin. It's also called the viewpoint or viewing position, camera position, or eye position. And after that, we have to specify a view up vector v, which defines the y view direction. And finally, for any 3D space, it's required to assign a direction for one of the remaining two coordinate axes, which is x view and z view in this case. And typically, we accomplish this with defining a second vector that defines the z view axis that I'm going to talk about next. Now I'm going to talk about a 3D viewing parameter called view plane. So because the viewing direction is usually along the z-view axis, the view plane is normally assumed to be perpendicular to this axis. Therefore, the orientation of the view plane as well as the direction of the positive z-view axis can be determined with a view plane normal vector called n. So in addition, we have a scalar parameter that is used to set the position of the view plane at the same coordinate value ZVP along with the ZView axis, as we can see in figure 9. So this parameter value is usually specified as a distance from the viewing origin along with the direction of viewing. And this view plane is always going to be perpendicular to X view, Y view plane. And also the vector n can be specified in various ways. In some graphic system, the direction for n is defined to be along the line from world coordinate origin to a selected point position. And in other systems, like in figure 10, the n can be, the direction of the n can be set from a reference point Pref to the viewing origin P naught. Okay, so now I'm going to talk about the UVN viewing coordinate system. And basically, in this coordinate reference frame, the direction of z view axis is going to be along the view plane normal vector n, and direction of y view axis is going to be along the view up vector v, and direction of x view axis can be determined by calculating the vector cross product of v and n. So if we take three unit vectors with the help of these ve- this view plane normal vector n and view up vector v, we can get the direction of z view, y view, and x view. So these are the formulas to get the unit vectors n, u, and v. And from this, we can get a right-handed viewing system defined with unit vectors. Okay, so now let us talk about clipping planes. So clipping planes are used in 3D computer graphics in order to prevent the renderer to calculate surfaces that are at extreme distance from the viewer. So these can be like extremely close or extremely far away. So the plane is perpendicular to the camera a set distance away and occupies the entire viewport. So in the figure, we can see like there are two clipping planes. One is front clipping plane, the other one is back clipping plane. And everything that's in between these two planes are going to be rendered. And that is something the user will be able to see. Okay, so now let us talk about different kinds of 3D viewing effects. And basically, different views of objects in a scene can be obtained by varying the viewing parameters that we just talked about. So by fixing a viewing position, if the direction of n is changed, we can visualize the object around the viewing coordinate origin. And also a composite display made of multiple views from a fixed camera position can also be created upon varying n. So the first viewing effect I'm going to talk about is wide angle view. So a wide angle lens refers to a lens whose focal length is substantially smaller than the focal length of a normal lens for a given film plane. And this type of lens are capable of capturing more of the scene, and usually they are used in landscape photography or architecture, and we can see an example of wide angle view in this picture. So the next type of effect I'm going to talk about is panning. And in 3D modeling, in computer graphics, panning basically means moving parallel to the current view plane. In other words, the camera moves perpendicular to the direction it's pointed. And this direction does not change with time. And in this picture, we can see an example of panning. The camera actually tries to capture the taxi the entire time. So this gives us a panning effect. And the last type of viewing effect I'm going to discuss is walk around. So the concept of this walk around is very much similar to how we walk around a place and look at multiple things in a scene. And this allows us basically to capture the effect of interacting with different kind of objects and then exploring them from different angles. So if we take a look at this picture below, we can see different kinds of shapes of the same mug depending on from where we're observing it. So this gives us an walk around effect.
Alright, so now we'll talk about from world to viewing transformation. Now, what I mean by that is we're going to transform our viewing coordinates from world to user defined coordinates. How we do that is for that we have to look at Cartesian coordinate system first, and it's also our world coordinate system, basically with origin being at 0, 0, 0 in our 3D virtual space. Um, and the Cartesian coordinate system has three unit axes orthogonal to each other. It acts as a reference point of a 3D scene to which any other point on any other arbitrary coordinate system is measured to. Once this coordinate system is defined, we can create other Cartesian coordinate systems. As with points, these coordinate systems are defined by position in space, that's a translational value, and by three unit axes or vectors orthogonal to each other, which by definition what Cartesian coordinate systems are. So Let's take a look at an image to have a better understanding. With world coordinate system as our base, we can create other Cartesian coordinate systems. So here we are. The coordinate system in red with three axes orthogonal to each other, YW and XW being in the plane of the screen, and ZW axis is coming out of the plane towards you. We have another coordinate system in black which has again still same three coordinate axes which are orthogonal to each other, and their plane is different, but we have one thing, and that one thing is we can define this black coordinate system with respect to our red coordinate system in space. Let's see how we do that. So describing objects in viewing coordinates converted from world coordinates requires simple mathematical transformation in terms of translation and rotation. We use these two mathematical operations to superimpose viewing reference frame onto the world frame so that our transformation. So first we go ahead and translate the origin of this black coordinate system towards the center of our world coordinate system, center or origin I mean, and this is a translation, and other steps we do is to rotate this black coordinate system so that its axes align with our world coordinate system. In the image on our right, we can see first the purple one is brought to the origin of the black one, that's translation, and then some rotations are performed so that the axes are perfectly aligned with the black coordinate system. Building on top of that, assuming our origin is the view frame, origin of the view frame is defined at position x0, y0 and z0, we first translate this to the origin of the world frame by translation matrix T. And translation matrix T looks like this, with our point P0 represented in x0, y0, z0, and they are in negative, that means they are being translated back towards the origin. Next, we perform three rotations. Now the first rotation is around XW axis to bring ZV axis into XW ZW plane. When that has been done, we now rotate the black graph, or like the user coordinate system, around the YW axis to align ZV with ZW. Once that has been done, we rotate around ZW to align YV with YW, and since the axes are orthogonal to each other, XV is aligned with XW once we have done the third rotation. So math behind that looks like this, with the axis of rotation and different axes of rotation. So we have three different matrices. For around X we have the first one, and so on for Z, the last one. Finally, our resultant matrix would look like this, with all of these letters representing matrices that we just discussed. Another representation of the same operation will look like this, and for this, if you paid attention to the earlier part of this presentation by Proma, she mentioned what U, V and N vectors are, which are basically unit vectors representing the axis of the view coordinate system. And x0, y0, z0 is the origin of the view coordinate system with reference to world coordinate system. So once we have figured out u1, u2, u3, v1, v2, v3, n1, n2, n3, it's easy. We just use these two matrices to get our final resultant matrix, like this operation here. This is math. Feel free to pause the video to check out, to spend more time on this. But moving on, let's look at an example. And to keep it simple, we are doing it in a 2D system so that The amount of calculations need to be shown are less, but the principle remains the same. So we have our world coordinate system in the red and our user coordinate or viewing coordinate system in blue. As you can see, the origin of blue in terms of world coordinate system is at 4, 3. That's also called P0. And then the point P, where the point at 5, 5 in terms of world coordinate system, that point in terms of viewing coordinate system is somewhere around 1.8 to 1.75, depending on that coordinate system. So as we can see, it's the same point, but the values are different because the reference and the origin and their orientation is different. So now we want to bring them to the world coordinate system so that everything can be standardized in a sense. So moving on, we have the translation matrix is simple, minus x0 minus y0. So it was 4, 3, the point P43 gets translated to origin by this matrix. And now if you look at it, our axes are still not aligned, they are at an angle of 30 degrees. So the next step we need to perform is perform a rotation. So doing that, a rotation matrix comes out to be this point here, this rotation matrix here, which is easily you can see is cos 30, sin 30, minus sin 30 and cos 30, the values in the matrix. Once that has been done, our viewing system gets aligned perfectly with the world view system, and in 3D you do the same things, just that you have to do these rotations multiple times, 3 times to be exact. We just had to do it 1 time here. That's the only difference, but the principle remains the same. Now once we have understood how we translate the world system to viewing transformation, we can go ahead and look at projections. In projections, we have a coordinate system that allows us to project stuff in 3D world onto a 2D screen, right? How to do that is what we are going to see here. So if you see the image on the left, it's a 3D image, but if you project it on a 2D screen, it looks like something like what's in the square here. You get only one side of the view and it's flat. To better understand, here's another example on the right, and based on the place we are looking at it from, we get a very different image of it, right? So if you look at from the bottom, it's a circle. If you look at it from the left, it's more like a parallelogram. If you look at it from the top, it'll be like a frustum. So that is projection onto different planes. Now projection is of 2 types. In parallel projection, the coordinate positions are transferred to view plane along parallel lines. This is very important. So let's say P1, P2 is a line in 3D space and we want to project it on our view plane. They'll be projected along the parallel lines. So P1 dash and P2 dash would represent the projection on the view plane. Perspective projection is different, where coordinates are transferred to view plane along the lines that converge at a point. So it's different, and as you can see in the graph, in the image here, it's different. The lines are not parallel and they converge at a point. That point could be viewer's eye or anything for that matter. We can choose that, and choosing that point will affect how the points are represented on our view plane. Now let's talk about orthogonal 3D viewing projections. They are a type of parallel projection. Various views can be taken from parallel to principal faces. For example, we could have a front view, a side view, a top view. The key remains here that they are projected parallel to the lines, parallel lines from the object to the plane. Now there's a special type of orthogonal projection that is called axonometric orthogonal projections. In this, you still do the same thing as you project along parallel lines, but the object is oriented in such a way that you can see more than one faces of it. So the symmetry is maintained in terms of parallel lines, but you can see more than one face of it. In that, there's also another spatial kind, that is isometric projection, which is most common form of axonometric projection, that are generated by aligning projection plane so that it intersects the principal axis at the same distance from the origin. So if we think of a plane, and if we think of those 3D axes, now you try to position the plane to intersect all of those axes such that the points of intersection are equidistant from the origin. Another beautiful example to help you understand how projections work and how different viewing angles would lead to different images, we have this piece of art. Here you can see on the left side, it just looks like a bunch of pieces hung around by wires, but if you move around and change your viewing angle, you can see it starts to look like a face. It's the same object, just the viewing angle is changed, and if we consider this as a viewing plane, so you can see how projections can vary based on the angle we look at that from. Now, in orthogonal 3D viewing projections, projection coordinates are a big thing. Depending on the projection direction, if projection direction is parallel to z-axis, then xp is equal to x and yp is equal to y. xp and yp are the projection points, and x and y are points on the view plane. So if we see here in this graph of axes, 3 axes, z view axis is the axis along which our viewing axis is, and the plane is intersecting z view, and it's parallel to xy plane, x view and y view plane. So if we project a point from this coordinate system to this viewing plane, the point would just simply have the information of x and y because it's parallel to those, and the z value would not matter because we are not showing depth because plane is only 2D and you cannot have knowledge of third dimension in 2D. But the key thing is sometimes the z coordinate information is still kept alive for visibility detection processes, and we would learn more about those further in our presentation. Another look at projection coordinates. So let's say xp, yp, zp was our point to be projected, and xyz was our point which is being projected. It's being projected on a plane that is parallel to xy, and z is our viewing direction. So as you can see, xp is just equal to x right here because it's parallel to that plane. Y is also the same, but z value is equal to 0 because there's no height in a plane. And this is a mathematical representation in terms of metrics for the same on the right. Moving on. Orthogonal projection view volume and clipping. It's a very interesting topic. So if you see edges of the clipping window in 2D, right, restrict the limits of x and y on the view plane. How do we interact with clipping windows in 3D? It's the same as just discussed in the viewing coordinates of projections. You have a plane, and inside that plane is there's a clipping window. So you can apply the same clipping algorithms as you do with a 2D picture once you have projected the points from 3D onto a 2D plane. So the images below are just an example. Now there's the extra thing about 3D projections compared to 2D is the limits of the window define the clipping region, but there's also a concept called orthogonal projection view volume. Now what is view volume? The volume can be defined by two clipping planes let us say near and far, in the direction of the view. So if z view was our direction of the view, we can have two planes parallel to the viewing plane, one of which is near to us and one of which is far to us. And the volume between those planes is our orthogonal projection view volume. Now view volume is a cube that is defined by the planes x plus minus 1, y plus 1, y minus 1, z plus 1, z minus 1. So between these planes is our view volume, and x, y, z is the point of our projection of the object we want to project. Now, since we have this cube of x plus minus 1, y plus minus 1, and z plus minus 1, there can be different user-defined view volumes which do not conform to this standard canonical side 2 view volume cube that we have. So there are ways to convert the user-defined volumes into the standard canonical view volume, and this process is called orthogonal projection normalization. The steps to do that are very simple. The first step is you translate the midpoint of the view volume defined by the user to the origin, so x0, y0, z0, and then you scale the view volume dimensions to the length of 2. So if your viewing volume is a rectangle, and to convert it to our standard cube, you will translate the center point of that rectangle to 0, 0, 0, and then you would scale each of its sides such that it fits into our view volume on a scale of 2. To do that, it's very simple. We just use this translation and scaling matrix, where the diagonal represents the scaling factor and the last column represents the translation of the midpoint to the center. Now, normalized projection coordinates are converted to device coordinates for display. That's why they are useful. Projection normalization ensures that all projections are converted to orthogonal projections by first distorting the objects such that the orthogonal projection of the distorted object is the same as the desired projection of the original objects. The normalization process allows us to carry parallel and perspective projections with same pipeline. This is an important thing, and that's why normalization are done, and it's a very powerful tool, so that now you can basically normalize any view volume to the standard volume, and then you can go ahead and project it on any screen just by converting the standard volume to the coordinates of the display. Thank you, that does it for me, and Cole will take over from here for the next part. These are the references used for day 1.
Continuing on from orthogonal projections, oblique parallel projections are obtained when the projection path is not perpendicular to the viewing plane. In a sense, this is a more general form of the orthogonal projection, in the case that the base case for the oblique parallel projection is the orthogonal projection. I'll go over more of this a little later. But unlike the orthogonal projection, the oblique parallel projection shows object surfaces which are not perpendicular to the view plane. It's not as convincing to the human eye as the perspective projection we're going to cover later, but it allows you to see more than simply the orthogonal projection. So an example of this can be seen on the bottom here. The bottom left is an example of the orthogonal or the oblique projection, but taken from above. So the dashed lines are the projection path, and the viewing plane is shown there. And you can see all of the descriptors of the object are projected along those dotted lines, which are running parallel. And on the right, you can see the produced image. So let's go into some of the math, and then I'll show you some examples. In architectural and engineering drawings, the oblique parallel projection is parameterized using two angles, alpha and theta. And using these two angles, you can use these equations, and they produce these projection coordinates x sub p and y sub p. But these are somewhat archaic to me, so I'm going to break these equations down for you real quickly. So starting with these two, x sub p and y sub p. Looking on the left, we see the triangle formed between the projected coordinates x sub p, y sub p, z sub p, the world coordinates x, y, and z, and the projected coordinates if we had used a simple orthonormal projection, x, y, z sub vp. Now, you see that this forms a right triangle with the red lines and the blue lines in the L, and the y component is L sine phi, and the x component is L cosine phi using our SOHCAHTOA rules. And we can see that x sub p is equal to x plus L cosine phi, and y sub p is equal to y plus L sine phi. So that explains these equations. Now, for the other, we have the triangle formed between these 3 points. Using, again, SOHCAHTOA, we get that tan alpha is equal to z sub vp minus z over L. And rearranging that with some algebra, we can see that L is equal to z sub vp minus z over tan alpha. And if we create this variable, L1 equal to cotangent alpha, then we can replace that as equal to L1 times z sub vp minus z. And the L1 is what would happen if the length of z sub vp minus z is 1. It's kind of the unit case. So combining these together, we get the equation x sub p is equal to x plus L1 times z sub vp minus z cosine phi, and y sub p equal to y plus L1 z sub vp minus z sine phi. Now, the previous formulations were expressed as equations, but in the computer world, we would like to use a vector. So we can do this with a vector we'll call v sub b. And we're going to represent, this is a unit vector with x, y, and z coordinates. And I've got them depicted here with the x being blue, the y being red, and the z being green. And v sub p just points from each point to the viewing plane along the line that it's going to be projected along. So I'm going to extract some relationships from this, and then we can use a matrix transformation using this vector like we've been doing with the previous projections. So the first useful thing that we get is this helpful relationship. I'm going to go over how we can get it. So looking at the x, we can use the law of similar triangles by drawing a triangle from the world point to the orthonormal projected point, and the location on the horizon going down from the projected point. You can see these similar triangles. The ratio is going to be preserved on the lengths of xp minus x. It's going to be equal to vpx, and vp minus z is equal to vpz. You get the exact same thing for the bottom relation, except with the y. You draw a slightly different triangle, but you get the same relationship. Now, using this, it happens that this equals, the top relation equals L1 cosine phi, and the bottom relationship equals L1 sine phi. The reason that you can get this is x of p minus x is equal to cosine phi over L. And from our previous relationship, z sub vp minus z is equal to tan theta, or tan alpha over L. And when you combine those together, you get L1 cosine phi. And the same for the bottom, we get L1 sine phi. And combining all of these together, you get x sub p is equal to x plus z sub vp minus z times vpx over vpz. and y sub p is equal to y plus v sub z sub vp minus z times v sub py over v sub pac. Now, there are two common selections for alpha which provide unique properties under the oblique parallel projection. That would be the Cavalier projection, alpha equal to 45 degrees, and the cabinet projection, alpha equal to about 63.4 degrees. And the way that these are special is the Cavalier projection is going to preserve the lengths on all lines that are parallel to the viewing plane, and the cabinet projection are going to divide all lengths by half. The reason that this occurs is because L is equal to z sub vp minus z over tan alpha, and at alpha equals 45, tangent is equal to 1, and alpha is equal to 63.4, tangent is equal to 1/2. Now, using the vector formulas, we can create this transformation matrix, which can be combined with the previous matrices to put these in the put the projection in the viewing plane. So you see here on the right-hand side, it's kind of ugly, but as with all the others, it just happens in the background. But this is how it was derived from these two equations that we got using the triangle relationships and the vector relationship. Back to the Cavalier projection. Again, just going over, the Cavalier projection uses an alpha equal to 45 degrees, and since tan 45 is equal to 1, the length of L from the length of L is preserved. Therefore, all lines parallel to the projection plane show no change in length in the new image. A and B show two different Cavalier projections of a rectangle of a cube. You'll notice there was a weird lengthening of the lines. This is an artifact of this projection type. The lines going from the front face to the back face. And these two values of phi are the angle downward to the object that we're projecting. So with 45, you can see more of the top, whereas 30 is more focused on the front side. The cabinet projection uses alpha equal to 63.4, and since tan of 63.4 is approximately 2, the length of each length on the cube is cut in half for lines that are parallel to the projection plane. You can see that this is a somewhat more realistic view of it. It looks more natural. Now, because the projection is oblique, the view volume is also oblique. It forms a parallelepiped head. And you can see here that on the left-hand side what that would look like. Now, the M oblique matrix that we derived earlier is a shearing transformation. And the lucky thing is, after applying the shearing transformation, you get a orthogonal projection. So after this, you get to use all of the previous work for clipping and for viewing and for normalization from the orthogonal projections. Moving on, we'll talk about the perspective projection. This is a more realistic form of projection as it approximates a camera or our eyes. But rather than projecting every point along the same vector to a viewing plane, you project each point to the center of a projection, to a center of projection or a projection reference point. Now, this is more natural because near objects of the same size are bigger than objects further away of the same size. So you can see here in this diagram, the horizontal line is the same length in both directions, but the closer one when projected to the viewing plane is longer than the one that's further away. And this is how we perceive the world. This is, in a sense, another depth indicator that our brains use for binocular vision. Of course, we have natural stereo vision because we have two eyeballs, but if you close an eye or you happen to only have one eye, you can still have some sense of depth due to your knowledge of the relative sizes of things and the effective perspective. Now, the center projection is a singular point that all other points will be projected to. It can be any point, but many graphics packages often restrict this position to make the calculations easier. So in this picture here, we have the world coordinate P equal to x, y, z, the projected points x sub p, y sub p, z sub vp on the viewing plane, and the center of projection, which is x, y, z sub prp. Now, we're going to derive some relationships for this so that we can create a matrix just like the previous transformations, but we're going to start by parameterizing the line from the center of projection, or the projection reference point, to the world coordinate. So on the bottom right hand side, we can see x prime is equal to x minus prp times u. Similar relationships for y and z, and u can range from 0 to 1. Now when u is equal to 0, we are at the world coordinate, and when u is equal to 1, we are at the projection reference point. And any value of u in between produces the point on the projection that lies on that plane, or on that line between the two. Now, if we assume that z prime is on the view plane, then z prime is equal to z sub vp. And from that, we can solve for u using algebra, and we'll get u is equal to z sub vp minus z over z sub prp minus z. Plugging this into the other equations, we get this formulation for calculating x sub p and y sub p. Now, from this perspective, there's three different ways of creating perspective projections. There are called 1, 2, and 3 point perspective, and these labels apply to the number of vanishing points that are in the scene. Now, the vanishing point is a point where all lines that are not parallel to the viewing plane will converge. And depending on the number of vanishing points, different lines will converge on them, or they could all converge on one. I'll go into more details in the next slide. So here, the number of vanishing points depends on the number of principal axes that are intersected by the viewing plane. So if you had a viewing plane that was parallel to the zy axis and intersected the x-axis, then you would have a single vanishing point, and this would be 1 point perspective. If you had a plane that intersected the xy axis, xy principal axes, but never intersected with the z-axis, then you would have 2 point perspective. And if you had a viewing plane that intersected all three of the principal axes, then you'd have 3 point perspective. Now here's an example of 1 point perspective. As said before, you have a single vanishing point, and the viewing plane only intersects a single axis. And that produces images like this, where you have a single vanishing point on the horizon, and all points that are not parallel to the viewing plane converge on that. So you see that the faces of the front and back faces of this cube, the lines are not distorted. However, the lines connecting the front face to the back face are distorted, and they converge on this vanishing point. Here's an example of an image with this showing 1 point perspective. So you see at this road, all of the lines are converging on this 1 point in the center of the image. Here they are highlighted. So you see the blue line is the horizon line, and the red lines are just a few of the lines that I've highlighted that you can see they're converging on this vanishing point. Of course, if you're standing on this road, the lines are perfectly parallel, but because of the perspective projection, they appear to converge. 2 point perspective is when the viewing plane intersects with two principal axes and has two vanishing points. And it's often used for side views of buildings. And it gives a kind of like an angular appearance. So here's a city block that's been specifically drawn to show 2 point perspective. And here it is highlighted. So you see the horizon line where the 2 points are connected. I don't have it highlighted here, but you can see it in the background. And you have two vanishing points. And all of the points on the buildings that aren't parallel to the viewing plane converge on these points. Finally, we have three-point perspective. This is when the viewing plane intersects all three principal axes and has three vanishing points. And this isn't used as often as two-point perspective. So here's an example image of a tower block object with three-point perspective. Now you see you have two vanishing points on the horizon line, and you have one vanishing point above the object. And what this does is it gives you information about height distance as well as horizontal distance. So you see the faces of the building that are closer to you get smaller as they move away, and also the bottom of the building is larger than the top of the building because, again, this gives the solution of distance from the observer.
Afternoon, Jaideep, and I'm starting from view volume for perspective projection. And view volume is created by specifying the position of a rectangular clipping window on the view plane. Here is the clipping window, and here is the center of projection. And the top, bottom, and side of a view volumes are planes through the window edges that all intersect at one point known as projection reference point. This is the projection reference point, and this forms a view volume that is an infinite rectangular pyramid with apex at center of projection, and it is also known and referred as pyramid of vision because it looks like a pyramid, bent pyramid. And the above figure shows the pyramid of view volume for perspective projection. And to that view volume thing, if we add near and far clipping planes that are perpendicular to the z axis, we chop off the parts that are infinite perspective projection view volume to form a truncated pyramid, which is basically known as view volume. This is the view volume. Now we can see the one without dotted lines is the truncated pyramid and also known as frustum, which is view volume. And now we will move on to the clipping ready transformation. We can use a three-dimensional homogeneous coordinate representation to express the perspective projection equations. Basically, if we divide a Cartesian equation with homogeneous parameter, we will obtain with the homogeneous coordinate. Here the xh and yh parameters are same from the parallel projections, and the perspective projection transformation of viewing coordinate position is then accomplished in like two steps. First, we have to calculate the homogeneous coordinate using perspective projection matrix and normal column matrix representation. Here in the above equation, pH is the finding for homogeneous coordinates, and MPers refers to the perspective projection matrix, and P refers to the column projection matrix. And being the normal procedure of substitution of xh and yh, we must also structure the matrix preserve depth information. Otherwise, the z coordinate is distorted and homogeneous division parameter h. This can be done by setting the elements for z transformation so as to normalize the perspective projection. Here MPer stands for perspective projection matrix. Here in the perspective projection matrix, we have the two unknown terms known as Sz and Tz. Those are scaling and translation factors for normalizing the projected value z coordinates. Basically, the Sz and Tz depends on the range of normalization which we select. And now we are moving to another topic known as normalizing the view volume. Basically, normalizing the view volume is a transformation which normalizes the view frustum from perspective projection to the conical view frustum. Here we can see that clipping before normalization. This is the frustum view volume, and it is transformed into the normalized view volume. So when we divide the homogeneous coordinates by homogeneous parameter h, we obtain with the orthogonal projection coordinates, and the figure refers to the normalization transformation from a transformed perspective projection view volume to the symmetric normalized cube. Yeah, and the final step in the perspective transformation process is to map the parallelopipe to the normalized view volume. We follow the normalization procedure is similar for the parallel projection and perspective projection as well. And the transformed frustum view volume, which is rectangle parallelopipe, is mapped with symmetric normalized cube within a left-hand reference frame. And we have already included a normalization parameter z coordinates in the perspective projection matrix, but still we need to determine the values for the parameters when we transform to the symmetric normalization cube. Also, we need to determine the normalization transformation parameters for x and y coordinates, because the center line of the rectangle parallelopipe view volume is now z view axis. No translation is needed if x and y normalization transformations. And we use scaling matrix. The scaling matrix is determined below. This is a scaling matrix which have Sx and Sy. For using the following operation, or for finding the normalized perspective projection matrix, we need two matrices. We have to multiply them. Those two are the oblique perspective matrix and scaling matrix, which we have showed in the earlier slide. And by multiplying that, we'll obtain with the normalized perspective projection matrix. Now we'll move on to another topic known as 3D clipping. Basically, 3D clipping, just the definition of a clipping is it's a method to selectively enable or disable the rendering operations with defined region of interest. Basically, clipping means before projecting, we need to eliminate the portion of the scene that is outside the viewing frustum. And it is also same as the 2D clipping, and it can be achieved by discarding objects that are behind the camera or outside the field. And these are the steps for 3D clipping algorithm. Applying 3D clipping algorithm to the normalized boundaries allows the viewing pipeline and the clipping procedures to be implemented in highly efficient way. All the device independent transformations are concatenated and applied before executing the clipping routines, and each of the clipping boundaries for the normalized view volume is a plane that is parallel to the Cartesian planes. Depending on the normalized view volume being a unit cube of length 2, the clipping parameters have coordinate positions at either 0 to in between 0 and 1, or at -1 and 1. The equations for three-dimensional clipping planes are the minimum x coordinate is -1, the maximum x coordinate is 1, the minimum y coordinate is -1, and maximum y coordinate is 1, and it is similar for z coordinate as well. And the x and y clipping boundaries are normalized limits for the clipping window, and the z clipping boundaries are the normalized position for the near and far clipping planes, which we showed. The near and far clipping planes are apart from the clipping window. Clipping algorithms for three-dimensional viewing identify save all the object selections within the normalized view volume for display on the output device. And the algorithms are now extensions of two-dimensional methods using normalized boundary planes of a view volume instead of a straight line boundaries of a normalized clipping plane. Normalizing strategy basically makes the clipping efficient. So yeah, that's all for 3D clipping algorithm. And this is the use of homogeneous coordinates. As I stated earlier, homogeneous coordinates has a homogeneous parameter h. If the value of h is 1, then it is Cartesian projection coordinates. And it is also same for the parallel projection coordinates, but the perspective projection coordinates differ from the parallel projection coordinates from the homogeneous parameter, which is a function of z coordinate. And the perspective projection homogeneous parameter can even be negative if it is beyond the projection reference point. Then the homogeneous parameter can also be the negative. It can be positive or negative. That depends on the position of the projection reference point. It is either behind or ahead, like that. And an effect and applying the clipping routines to the homogeneous coordinates is an effective method, so which everyone will use. And because of all view volumes can be converted into normalized cube, a single clipping procedure can be implemented in hardware clip homogeneous coordinates against the normalized clipping planes. And this is a three-dimensional homogeneous coordinate plane. If the value of homogeneous parameter is 1, then it will be the Cartesian projection coordinate. And after a position has passed through the geometric viewing and the projection transformation, this is now the homogeneous form, which can be obtained by multiplying the normalized perspective projection with the homogeneous coordinates, where the m norm pers refers to the normalized perspective projection matrix. And this is the last topic, which is the line and plane intersection. In the below figure, we can see a plane is intersected with the line, but this is in the 3D clipping part, so that we have to clip a line segment. This is an example for clipping a line segment from a intersection of line and plane. A clipping plane can be specified with the plane parameters A, B, C, and D. The plane that divides three dimensions into two parts, assuming that the objects behind the plane are to be clipped. Let us assume the spatial position xyz that satisfies the following inequality for the given plane and line. And the figure shows the clipping line segment against the plane with normal vector n. N has a coordinates of ABC. And as an example, if we consider parameter array has a values of ABCD as 1, 0, 0, 8, then the coordinate position satisfying the equation x plus 8 less than 0, which is also equal to the x less than minus 8. So the line beyond 8 is clipped off. We can say that to be frankly speaking, the line beyond the plane means which is from P to P1, which is got clipped off. And to clip a line segment, we first tested two endpoints to see if the line is completely behind the clipping plane or the line is completely in the front plane. And these are the references that we are used for perspective projection and parallel projections. That's it from my side. Thank you.